All right, so let's pick up where we left off. Determine whether each of the series converges or diverges. So our first example, we've got the summation from n equals 1 to infinity of 1 over the cube root of n. And this is pretty awesome because this is a p-series test. I can rewrite this summation from n equals 1 to infinity of 1 over n to the 1/3 power. And that is positive and is in the denominator, so we can use a p-series test. And we're going to take a look at that p-value. That p-value is equal to 1/3, which of course is less than 1. And if we're looking back at our notes that we have, if it's greater than 0 but less than 1, then it diverges. So we're going to say this diverges by the p-series test. And you notice that each time I write my justification, I'm writing y. And that just tells us that you know what you're talking about and why you're talking about it. So it does diverge by the p-series test. All right, our next example, the summation from n equals 1 to infinity of 1 over n to the 5/4. And this is already in that p-series notation for us. And this is why we call it the eyeball toss. You just go, hey, p is 5/4 and 5/4 is greater than 1. That means our whole series converges by the p-series test. So let's take a look at a couple of ways the AP has assessed this previously. Now you guys are in a unique situation, so we'll take a look at that in terms of what you guys have. Your exam is all going to be no multiple choice, so we're going to do this pretending that these are not here. And it just says which of the following series diverges. So one of the things to look for first is the variable and where that is. These are all in terms of the variable n. So anything with our variable n, I'm going to highlight really quick just because that's what we're looking for. Where that n is located will tell us how we can do this. So let's take a look at the first one. We've got the sine of 2 over pi to the nth power. So this means it's exponential, and if it's exponential, we can look to see if we can write it as a geometric series. And sure enough, hey, if a sub 1 is 1, then this is our r value to the nth power. So our r value is equal to the sine of 2 over pi. And I don't quite know what the sine of 2 is off the top of my head. I know the sine of 3.14, I know the sine of pi halves, but the sine of 2 is kind of hanging out there in between, but I know what it's bound between. Sine has to be bigger than -1, whatever it is, and sine has to be less than +1. So the sine of 2's got to fall somewhere in between these. And I'm not just having sine of 2 by itself, I'm dividing it by pi. So if I'm dividing 1 by pi, I know that that's going to be some number that's got to be less than 1. And if it's less than 1, then this one converges by our geometric series test. So I know it's not number 1. So if I were doing multiple choice, hey, I could narrow it down to just A and D right away. But it's not gonna be, so let's take a look at another one. We've got the summation from n equals 1 to infinity of the cube root of n. Hey, we just did that. That's a p-series test. P is 1/3, which is less than 1, which means this diverges by the p-series test. Whoop. So I know 2 is an option in play. And let's take a look at the third one. This has an e to the nth power and an e to the nth power plus 1. I do not know exactly how I can write that as a geometric, because I really can't, because 1 is not taking to the power, and it's not a p-series. So let's use the nth term, because we're just checking for divergence. So we're going to take a look at the limit as n goes to infinity of e to the n over e to the n plus 1. So if we're taking a look at those and dividing it by e to the nth, and e to the nth, and e to the nth, as n goes to infinity, I get 1 over 1 plus 0, which equals 1, which doesn't equal 0, which means that diverges. So 2 and 3 both diverge. Here's another one. What are all values of p for which the integral from 1 to infinity of 1 over x to the 2p dx converges? And this doesn't quite look like a summation, but one of the things that they're asking you to recognize is that this is our formula for what a summation is. That summation form of an integral, those are two things that'll flip-flop back and forth in between. So I've got x, and I've got 2 to the 2p. So it kind of looks like a p-series. So this one, we're looking for values that converge, and for a p-series, it'll converge as long as the exponent is greater than 1. So I need p to be greater than 1/2. Here's another one. Let f be positive, continuous, and decreasing. And those are things that should be triggering in your head that, hey, they're talking about the integral test. And the integral test such that if the summation from a sub n converges to k, which of the following must be true? So if we're using the integral test, we also need our integral from 1 to infinity to also converge, and it's going to converge to a number. So I can cross off letter C because it can't diverge. And I'm looking at this, I can also cross off letter A, because that's a nth term test for divergence, but we're looking for convergence. I can cross off letter B, because there's an N up here, and that's not what we're looking for. So what we're looking for is a difference between these two. And we talked about this earlier, that the limit, your integral of your function, needs to equal some real number. But we said the real number does not equal the number that your summation equals to. And this is really diving into, do you know the definition of these? So between D and E, I can cross off letter E because that's not guaranteed. All I need to be true is letter D. Here's another one. For what values of P are the infinite series n equals 1 to infinity of n over n to the P plus 1, does it converge? So taking a look at this one, it doesn't quite look like a p-series, but this is making me think it's a p-series, and so are my answer choices. So let's see how we can write this as a p-series. If we have the function n over n to the p plus 1, that's going to be very similar, and we'll talk about this more explicitly a little bit later in our notes. It's going to be very similar to this, because when we're having that +1, it's doing things that are so small that it's really not changing the value of this. And that's really what we're going to continue to talk about, how functions are acting and how the certain parts are making them faster or slower or not impacting them as much. So just to show you what I'm talking about, I've got a Desmos screen up. Here it is with just x and x squared plus 1. So we're plugging in 2 for our p-value. If I plug in x over x squared, as I go to infinity, there's really no difference there what our values is as we're going out. And I can change that p-value, let's say x to the 4th, and this becomes x to the 4th. It gets even closer, faster, as I get further and further out here. What if it's x to the 7th and x to the 7th? If it's x to the 2nd and x to the 2nd again, oops, that was a subscript. So whatever we're doing, it's going to be pretty close to what we've got. So if we take a look at that, I can rewrite that as the summation from n equals 1 to infinity, and that becomes 1 over n to the p minus 1 using exponent rules. Same base, subtract the exponents. And since I'm keeping it in the denominator, that's why it's p minus 1. If I would take it to the numerator, it would be 1 minus p. So if I have this, now it's in a p-series form, and in order for this to converge, I need p minus 1 to be greater than 1. So I'm going to add 1 to both sides, and p has to be greater than 2. And look again, if it were a multiple choice, they're really testing, do you know the difference? Here are your 2 options, and we don't want it to include that greater than or equal to 1. We just want it to be greater than 2. So give your homework a shot tonight. Let me know if you've got questions, and we'll talk to you guys later.